All right, so in this part, we're going to prove the intermediate value theorem for continuous functions. This is one of the kind of more famous theorems from intro real analysis classes, not to be confused with the mean value theorem, which will come much later, and that has to do with integrals. The intermediate value theorem is basically, in a nutshell, sort of colloquially, just the statement that continuous functions don't skip values. So if the function has a certain value at one point in the domain and then a different value at a different point in the domain, if all the points in between those two places in the domain are also in the domain, then the function is not allowed to skip values, basically. So it has to hit every value in between those two values, basically. So that's kind of the informal statement. Let me just state the theorem itself. So theorem 18.2. This is the intermediate value theorem. So if f is a continuous function on an interval I, then f has the intermediate value property on I, meaning if A and B are elements of I with A less than B, and Y is between f of A and f of B. Yeah. Also, this is assuming, okay, whatever. So, i.e., f of A less than Y less than f of B, or f of B less than Y less than f of A. Okay, so that's what it means for Y to be between f of A and f of B. And now notice that this assumption implicitly also means that we're assuming that f of A and f of B are not the same number, okay? So if f of B and f of A are the same, this is all bets are off, basically. Like, the intermediate value theorem just doesn't apply to those situations. Okay, so anyway, so we're assuming that they're different values, and then whichever order they're in, y is somewhere between them, okay? So if y is in between f of A and f of B, then the intermediate value theorem says, or the intermediate value property dictates that then there exists an x in AB such that f of x equals y. Okay? And I do really want to draw your attention to the fact that the intermediate value property, or the intermediate value theorem, tells us that there's an x in the open interval AB, all right? I mean, obviously, x can't equal A or B if we assume that y is strictly in between f of A and f of B, because, if x was A, then f of x would be f of A, and similarly, if x was B, f of x would be f of B, and, we need f of x equals y. That's incompatible with those possibilities. But, I've just seen people try to apply the intermediate value theorem where they relax all of these inequalities, and then they change this to this, and or without doing that, I guess. And you have to be careful about that. Okay, just be careful. So these are strict. So there, I mean, you can mess around with it a little bit, but you know, only in certain ways, I guess. Okay, anyway, so I'm gonna go to a new page and I'm gonna sort of draw a sketch to explain the idea of the proof here. All right, so here's kind of a picture of what's happening in the argument, I guess. And they have a picture in the book too that's like not too bad. But basically, okay, so the way the argument works is you sort of say like, well, we want to find a place where we expect f of x to equal y, right? And so it's, if you imagine, you know, if you almost imagine like what would happen if that never happened, basically, then it'd be like there'd be some places where f of x was less than y and some places where f of x was like greater than y. And so then you kind of imagine like, well, there has to be a transition in between those two areas, basically, right? And so one way to detect where that transition would happen would be to look at the supremum of the set of x values for which f of x is less than y, right? Because that's kind of like the biggest x value where f of x is less than y, or less than or equal to, and then like all the values after that have to be where f of x is greater than or equal to y, right? So there's like a transition that happens there. So that's actually how we do this. So like if we define S to be the set, so I can actually kind of like write up the proof here too. So take S to be the set of x for which f of x is less than y, and define x naught to be the supremum of S. Okay, so this is like x naught over here. Okay, right. Actually, maybe it'll be clearer if I write it up here. Okay, so x naught is the supremum of S. And notice that like, well, okay, for one thing, we're assuming without loss of generality that f of a is less than y, less than f of b, and not the other way around. So the other way is similar. Okay, so okay, so we made x naught, sorry, this is an equal sign. X naught is the supremum here, okay? So S, in this case, it's like 2 intervals, okay? Because notice that like the function can kind of dip above and below y many times. And of course, looking at the graph, well, we would say like, oh, well, you know, we could, why not pick x naught over here or here or here or here? The problem is in general, it's hard to describe what those places are. So we know we can find a value of x naught right here that works. So that's what we're just going to focus on, okay? So here's x naught. This is the supremum of S. S is these 2 open intervals, right? X naught is the supremum, so it's right here. And we expect for f of x naught to equal y, right? So let's kind of think about why that has to be true, right? F of x has to stay less than y on this side. So if it didn't go all the way up and kind of touch y right here, then it would have to like hit this line somewhere below. Okay, let's imagine that that happened actually. Okay. Then if you were to come from the other side, well, because it's continuous, it better hit the same point, right? But then you see there's a place where it crosses the line over here, and that's not allowed because f of x is supposed to be greater than or equal to y on this side, right? And if you really think about it formally in terms of the definition, if this happened where it sort of like somehow managed to meet this part of the graph below the value y, then you could take a sequence of points approaching x naught from this side, and all the values of f of xn, right? Xn would be a sequence approaching the points from this side. All the values of f of xn would have to be bigger than y, but then somehow the limit would end up being smaller than y, and that's like not allowed, right? So so it can't, this part can't end up hitting this line down here. And there's like a similar reason actually that this can't actually like end up over here. They both, this, the value, whatever the value of f, so this is, you know, f of x naught, whatever the value of f is at x naught kind of ties, it has to be like connected to both parts here, okay? And that's what we're going to exploit. So all right, sorry, I accidentally made kind of a little typo, but anyway, so basically what I was trying to say is that if you can take, you know, sequences approaching x naught from either side basically, and use the fact that on one side the values of f are less than or equal to y, and on the other side they're bigger than or equal to y, but they both have to end up converging to the same thing. Okay, so the sequence we construct from the left is, it goes like this. So for each n, choose Sn in S so that x naught minus 1 over n is less than or equal to Sn less than or equal to x naught. Okay? Yeah. Or let's say less than here. Not that it really matters, I don't think. But yeah, anyway, this is possible since x naught minus 1 over n is not an upper bound of S, right? A familiar piece of reasoning here, hopefully. So we can choose this sequence of points in S. That's what's vital, is to choose them in S, because then we can use the fact that f of Sn is less than or equal to y. So then xn, or sorry, not xn, Sn converges to x naught. So f of xn, or Sn converges to f of x naught. And then this is less than or equal to y. So f of x naught is less than or equal to y. Okay? So I'm going to leave that down there. So by taking a sequence going from this side, we found that f of x naught is less than or equal to y. So now we'll make a sequence going from the other side. So we will choose xn to be, and now since everything on this side is guaranteed, right? The reason that we had to specifically be careful about choosing stuff from S is that there are possibly areas to the left of, in this picture, for example, there are parts of the x-axis to the left of x naught where points may be in S or might not be in S. But we know that to the right of x naught, everything is not in S. So we don't have to be like picky about making sure to choose stuff that's not in S, because there are no points of S over here by construction. So xn, so then all we have to worry about is if xn, what we would like to do is take xn to be like x naught plus 1 over n, basically, right? And just approach from this side. The only issue is just like if 1 over n is too big, like if x naught is too close to b, then for small values of n, this might actually be bigger than b, right? But eventually, once n gets big enough, these values will get into this interval and everything will be fine. And so it doesn't really matter, but technically what we have to do is take this to be the minimum of b and x naught plus 1 over n. So that way, for the small values of n, right, when this is too big, this is bigger than b, we just pick b over and over and over again until finally this gets small enough that it starts, that it enters the interval, and then it starts approaching x naught from this side. So then xn approaches x naught, and f of xn is greater than or equal to y for all n. So the limit of f of xn is greater than or equal to y, and this is f of x naught. So is greater than or equal to y. Right? That means f of x naught equals y. Right? We established inequality in both directions. So yeah, that's, for this case, but like I said, the other direction is not really any different. So that's the intermediate value theorem. And I'm going to give the corollary that they give in the book here. And I'm just going to sort of describe it. I don't know if I'm going to go through it, fully in full detail, but so corollary 18.3 is, let's see, if f is a continuous function on an interval I, then f of I, which we define to be the set of f of x for x in I, is an interval or a single point. Okay. And so the idea here is just that, like, you know, regardless of whether the interval here, so when we say an interval, we mean like it could be, you know, something like AB, or it could be like AB, or it could be AB, or it could be AB, or it could be like A infinity, or it could be A infinity, you know, or like, yeah. So you see that there are, I guess there are two more possibilities for the left half, you know, infinite, and that, or three more, I guess. There's also R itself, all of R. So yeah, there's 9 total possibilities here of what, you know, what an interval can look like, I guess. But this kind of groups them all into one thing. And so when we say that this set is an interval, we just mean that it's of this form for one of these possibilities, basically, you know, that you have to be able to write this set as one of these possible sets, if it's not just a single point, at least. And again, notice that we're using the notation here of, you know, F, the image of an entire set, right, is a set. So this, you could also call this like the image of I under F. So basically this, you know, relies on the fact that if let's say, yeah, y naught and y1 are in J, then you know, basically y naught, y1, or let's say this entire thing is a subset of J, right? I.e., y is in J for all y between y naught and y1, right? So as you can imagine, if you just kind of like look at what are the biggest and smallest values in J, oh, of course, J here is also what we're calling, so say J is f of I, okay? So, you know, obviously J may not have a maximum or a minimum value. If I itself is not closed, right, then J, you know, J might be an open interval, but it doesn't matter. You can look at, you know, basically J is an interval with endpoints, infimum of J and supremum of J, which might also be infinite, by the way. So, you know, this all kind of works out if you allow these things to possibly be infinite, possibly be open or closed. It all works, basically. And this fact here, so this comes from the intermediate value theorem. Okay. So anyway, that's the corollary. I'm not going to go into too much more detail about that. And that's it for this part of the video. So I'll see you in the next part.